All right. You're welcome, everyone, to another session of machine learning. Having discussed all the theoretical aspects of machine learning as it relates to regression, today we're going to be looking at a live demonstration of a standalone AI software that was built upon supervised learning regression. So I'm going to open, it's a very simple software actually. It's a calculator specifically. So I'm going to share a window with you now to see one in action. Okay, so I believe you can see what is on the screen now.
Yes,
This
sir, we can see.
is,
Yes, sir.
yes, this is basically a calculator. It's exactly what it looks like, an actual calculator. But usually when programmers, when they are building a calculator, they use these mathematical libraries, like it's the normal mathematical libraries that have existed for many years. They use it to build a calculator to get very precise values for our calculation. But I took a different approach in building this software such that it's an AI that will be making those calculations in the background. Yeah, based on traditional machine learning models. So we're going to try a very simple calculation now. Now let's try 7 plus 3. We know 7 plus 3 is 10, but let's see what the AI is going to tell us what 7 plus 3 would be. 9.999, which is approximately 10. That's very accurate. Now, the reason is not giving us a very specific 10 value is because I'm not using a mathematical library for this AI calculator. What is happening at the background is the AI is making prediction based on a regression model in the background. So let's try another calculation. Let's try another addition. Let's try 65 plus, let's say 421. 65 plus 421 is actually 486. And the answer we got was 485.9983, which is very close. So these are the predictions that the machine learning model is making behind to give us this answer that we are looking at here on the board, on this software. So now let's try subtraction. Now let's try 587 minus 231. I'm actually comparing the value to a traditional calculator here with me, the one that was built with the mathematical libraries. This is 330, 356. Yes, it's also 356 on a traditional calculator. 356.005. That's what we got. That's what the AI predicted as the answer. So now let's try multiplication. Let's try 56 times 24. Okay, let's try one. 56 times 24. 56 times 24. You see, is actually 1,344. That's the actual answer. So you see that it is a little bit off here in terms of multiplication. We had 1285. That was what the AI predicted to be the answer. But in a traditional calculator, we got 1344. So it's far away from it, even though it might more or less, the accuracy is not that strong, but it's still close to an extent. So now let's try another multiplication. Let's try smaller number multiplication. Let's try 82. 82 times 82 times, let's say, times 9. Okay, 82 times 9. Let's see what it gives us. So 82 times 9 is actually 738, but we got 730 here. So is a bit off from it by eight scores for lower numbers. You see, as the number goes up, it becomes less accurate. So let's try a much bigger number, like 8976 or 75. 8975 multiplied by another big number, maybe 247 times 247. Let's try that and see. You see, it's very, very wrong. That is very, very wrong. The answer is actually 2,216,825. But we got 2,815 here as the answer. You can see that the multiplication accuracy is only good for smaller number multiplication. And we are going to find out why that is so very soon. Now, let's try division. Let's see how division works. Let's try 985. 985 divided by, let's say divided by 76. Divided by 76. What do we have? 24.63. The answer is actually 12.96 on a traditional calculator. So it's off for that. Okay, let's try a smaller number division. Now let's try 89, just 89. 89 divided by 3. Let's see if it's going to get that at least more accurately. We got 15. That was also off too. The answer is actually 29.66. So he's not so good at division, and he's also not so good at multiplication too. Let's try other mathematical operations also. Now let's try 65. Okay, let's try let's try power or square root. We should do square root. Let's do square root. So the square root of 25. The square root of 25 is meant to be 5. Okay, we got 5.2, which is very close. Let's try 64. Square root of 64 is 8. We got 7.9. That is also very, very close. Let's try 81. Square root of 81 is 9. We got 9.01. So he's very good at square roots to an extent for perfect squares. He's good at the square root of perfect squares. So let's try a number that is not a perfect square, like 894. 894. Let's find the square root of that, of 894. Square root of 894. The answer is actually 89.89. And we got 89. So he's also very good at even numbers that are not perfect squares too. He's very good at that. So that's very, very accurate. Now let's try another number like a huge number. 78923. 78923. Let's find the square root of this coming. 78923. Okay. That is also very, very accurate. It's actually 280.93, but it got 280.35. So it's really good at square roots. Let's try square. Let's try square. Now let's try 23 square. 23 square raised power 2. We got 5. It's actually 529, but it got 538 instead. So it's not that bad. So let's see how good it is at trigonometrical function like SOHCAHTOA. Let's try 85. Okay. Sine 85. Sine 85. 85. Then the sine of it. Okay, that's also very accurate. The answer is actually 0.996, but it gave us 0.997, which is very, very accurate. Let's try tan. I'm going to try tan 73. Tan 73 is 3.27. Let me clear this. 73. The tan of this, 3.27. Very accurate. Very, very accurate. It's almost like I did it with a traditional mathematical library. But it's an AI that is doing all of this. So let's try these roots. These roots that we are seeing here. Now let's say three roots, a big number, 236 rather. Let's try these roots. Coming. 36. Okay. So I'll just put it like this. 236 raised to power 1 over 36 raised to power 1 over That's the same thing as the root. The answer is actually 6.17. 6.17, but we got 9.3. So it's still very close. So now we are going to look at some things. Now what we want to figure out now is why is it so accurate with plus and minus, but multiplication and division is not really accurate like that. Square root seems to be very, very accurate. The square too, kind of, and the SOHCAHTOA trigonometrical is just on point, very, very accurate, but it's not accurate for multiplication and division. So now we are going to open up, first of all, we should first of all visualize the training data, the training data that was used for training this calculator. That should be the first thing we should look at to begin to investigate exactly what is going on. So I'm going to share the screen. So what you are seeing on your screen is GMP, is a statistical software. So we are going to look at this. Now let's look at the training data for addition. Why addition seems to be so accurate. So we open this and see. So for addition, let me share the window for addition. Good. So this is the addition window here. So we're going to create a graph. So you can see this is the training data set for the addition operation. You can see training data had. So this is value 1, value 2, then the results. So the AI will look at everything here. The machine learning model will look at all of these samples of data. If you scroll down, we are going to see that we have about 4,004 different values, 4,004 different calculations for the AI to learn how to do addition. Value 1 plus value 2 is equals to the result. So when you actually add it now, let's look at this one, for instance. 43 plus 17 is 60, which is correct. Minus 43 plus 37 is minus 9. So these are the things that the machine learning is actually learning from. This is the data set that is actually learning from. You may be wondering, how did I sit down to start typing all of this one by one and calculating? There are functions that I use in Excel. I actually use Excel for it. There was a way I did it. I generated random numbers in some instance, and then for the result, you just put is equals to A2 plus B2 for this result, and it's going to add everything up for you instead of you having to add it by yourself or even having to generate numbers by yourself. That's a function. That's a different topic entirely on Excel. You can do it on Excel. So now we are going to visualize this on the graph. For this addition graph, we're going to see how it looks like on our scatter plot, on our 3D scatter plot. The results will be the Y column. Value 1, value 2 would also be there. Okay, so I have to share this window also. There are multiple windows here that I've been. So I'll share this now. So now I'm sharing the scatter plot. You can also see the scatter plot of addition. So this is what the machine is actually trying to learn from. Everything, all these tiny, tiny dots that you are seeing here on this graph, they are the data points. All these tiny, tiny dots you are seeing here, they are the data points that we just visualized on our graph. And this is what the machine is going to learn from. So if we look at it from this angle, let me bring it down like this. If you look at it from this angle, value 1 plus value 2 will give us results on this axis. So this is the first dimension. This is the second dimension. Value 1 is the first dimension. Value 2 is the second dimension. And the result is plotted as the third dimension. The result is the dependent variable. It's depending on value 1 and value 2. Value 1 and value 2 are the independent variables to calculate the results. So if you look at it, if you look at this 3D scatter plot, you will notice that it's like a paper in a 3D space. That's what we can see here. So it's actually going to be very easy for it to learn it. So the machine will create an hyperplane. An hyperplane is just a 2D surface that would touch as much data points as possible. So when it creates an hyperplane, anytime we have a value 1 and a value 2, it's going to match it. Value 1, let's say value 1 is 0, and let's say value 1 is 0, and value 2 is also 0. Then it will not trace it down along the result axis. Whatever point it touches on the hyperplane will be the result that the AI is giving us. So this is one reason why this is very correct. It's very, very accurate, because looking at this alone, it's very easy for us to just put a sheet of paper there in the 3D space that will touch all of these points. That is how to fit a 3D graph by using a 2D plane, which is called an hyperplane. So if we are going to visualize the model file itself, come in, let me see. So we are going to visualize the model file of addition and see what is going on behind. So you would actually see that it's just a very simple multiple linear regression that is happening behind. Let me see if I can come in. So I'm coming. I want to open up the model. I want to open up the model file itself. Be under users. Okay, admin. Come in. Okay, under source. So I just want to like show a visualization of the actual AI calculator, good, of the actual model itself. And debug Windows, Apex. Okay. So the software for visualizing this model is called Netron. So we're going to use Netron now to visualize this. Let me see if it has already been opened. So it's loading. So we're going to open a model, Netron. Okay, good. Addition model. Okay, so I'm going to share this now. Good. So what you are seeing right now is the model, the addition model. That's what we are seeing now on the screen. It takes in value 1 and value 2 to figure out what the result is going to be. What you are seeing here now is the brain of the AI for addition alone. So if I open this is a node. The node takes in value 1 and value 2, does some transformation to it. Then it passes it to the next node. This is the next node, takes in the transformed value 1 and value 2 and outputs the features. The features are the things that it actually used to make calculations internally, which is still going to be, it's still coming from value 1 and value 2. Then this is the third node. This node is where the actual calculation is happening. If you look at this very closely, you will see where they wrote linear regression here. You can see this linear regression. That is what is written here. Now, remember what I told you about weight. The weight is just the coefficient or the slope. If you look at what is written here, it's 0.999999. That's the first weight. The second weight is also 0.999999. That's the second weight. And the bias is minus 0.00274. That is as good as saying 0. is as good as not having any bias at all. Now, if you think about this, if you remember the formula I showed you, y is equals to mx plus c. That m stands for the weight, while the c stands for the bias. But in our own case, because we have two features, value 1 and value 2, their weight is 0.99999 and 0.99, which is as good as saying 1. That weight is 1. So what this linear regression is telling us is that y is equals to value 1 plus value 2. Because this weight is just multiplying the features from value 1 and value 2. That is what is happening here. So you can see already that is the linear regression. Although the type of linear regression it is just a multiple linear regression, because we have value 1 and value 2. That is x1 and x2. That is going to multiply by this weight. And the bias is just a very tiny, very negligible negative bias, minus 0.0027 that you are seeing here. So that is what is happening. So every time I pass in value 1 and value 2 and I click on is equals to, it will run this thing, it will run this weight on those features and apply the bias to give us our result and send it back to us. You can see the output here. Let me click on this. The output is the features, which is going to be converted back to results. Whatever it takes in, it brings it out. That's the thing about machine learning model. Whatever it accepts that it's used to train it is what is going to push out. So it's a very simple model. So even if I type in 1 million plus 1 million, it's going to get the correct answer, because it's a very simple model. It's a multiple linear regression model. Very simple. There's no complexity about that. If I should open another model, like let me see, open recent. Let me see if it's in the recent. Like if I should open subtraction, have I opened subtraction before? It seems I have to like open it again. If I should open subtraction, what we are going to have in the weight, we are going to have one as negative and one as positive weight, because that actually makes sense if you think about it. So let me go back to the project folder and try and open. Let me try and open another one. Let's open the negative. I'm coming. It's not in the recent. I will have just opened it under recent. Okay, good. So this is okay. There's division, multiplication. There's no relative here. Okay. I'm coming. Instead of having to go through everything one by one, let me copy the parts and paste it in the netron. So we can just open it direct. Okay, good. So now I'm going to open this subtraction. That's a sub model. Let me open this subtraction. Okay. So I'll share this now for the sub model. Good. So what you are seeing here on the screen is a subtraction model. So this is what the machine learning model uses for subtraction. It takes value 1, it takes value 2, and then it gives us the results of it. Yeah. This is the first node here. Takes in value 1, value 2, output value 1, value 2. This one accepts it and converts it into features. The features will be used for the actual calculation. And this is the third node here. Takes in features, output features. You can see that for subtraction, it's also a linear regression that we're using. You can see what we have here is a linear regression too for subtraction. It's also a multiple linear regression. Remember what I told you about the weight for subtraction. The first weight is going to be positive, which is true, 0.99999, which is as good as saying 1. The second weight, you can see that is minus 1.000, which is as good as saying -1. And the bias is as good as just 0, just a negligible positive bias, 0.000503. So this linear regression is like saying y is equals to x1 minus x2, which makes sense for subtraction, because we are subtracting value 1 from value 2. That means the first weight there goes for the first feature, value 1. The second weight there goes for the second feature, value 2. So anytime I click on my calculator, value 1 minus value 2, and I press the equals to, is going to run this linear regression on it. by multiplying these weights on value 1 and then multiplying these weights on value 2 and then applying our bias, which is very negligible, to give us the results. That is the reason why we're always getting it correctly. So even if I put 2 million minus 1 million or 2 million minus 500,000, I'm going to get my accurate answer of 1.5 million because it's a very simple model. It's a linear regression model. Very simple. Just has two weights, a positive weight, a negative weight, and a negligible bias. Y is equals to x1 minus x2 plus c. The c is negligible. That's why it's 0 here. So you can see the real life application of multiple linear regression here for making prediction. Usually, when people are programming a calculator, they don't approach it this way because there's a library, there's a mathematical library for it. There's no need for them to approach it using an AI because it can easily be programmed using the ready-made mathematical libraries that exist already. So that's for subtraction. Now let's look at what addition is. Let's look at multiplication. Now we're going to find out why multiplication is not as accurate as other model. Okay, thank God there's multiplication here already. So I'm going to visualize multiplication now. Let's see what multiplication looks like. So this is for multiplication. Good. So this is the multiplication model here. It takes in value 1 and value 2 and gives us the results here. So this is the first node. This is the second node. And then the third node. Yeah. You can look at this. You can see that multiplication model is more complex than addition and subtraction because the features have been fused together. Because when you multiply value 1 times value 2 already, it is not going to be very easy to separate it again. You multiply value 1 times value 2 to get the result. You can't separate it in a very straightforward way. So this is where fast tree comes into place. Fast tree is also an algorithm, although I didn't really talk about it in the previous classes, but fast tree is also an algorithm. It's a machine learning algorithm you can use it for regression. You can also use it for classification, but in this case, we're using it for regression. What happens is that it kind of divides the data into very small compartments. It divides all the data into tiny compartments, tiny compartments. So any two value 1 and value 2 that falls within that compartment, it calculates the average. So what is doing is that it's just averaging it at different compartments. All these numbers that you are seeing here, they are just index. They are just index of the leaves. Yes, the first tree, just as you said, a tree has a leaf, right? So all these numbers that you're seeing there are just the leaves that is used for making a decision. It's called a decision tree. That's what it means. All of these are index of the leaves that is used for making decision. So the decision is to either cut it at a particular compartment, at another particular compartment, at another particular compartment. To show what I mean by this, let me visualize this multiplication data set. So I'm going to visualize the multiplication data set now. You see how it looks very, very weird. It doesn't look so straightforward. So what we have here on the screen is the multiplication data sets in 3D. You can see how it looks like. It looks like a cone that has been cut into two and has been spread out a little bit. You can see that there's like a curve here. It's like when you go to a chapel and you look at the top, there are some chapels that are designed this way that looks like a dome. It has a dome shape, kind of like a dome shape. So this is the data that the AI is going to use to learn the relationship between value 1 and value 2 to give us our results here. So in that fast tree that you're looking at, it's going to break all of this data into small compartments. Let me show it this way. I'm coming. Okay. Okay, it's going to like cut value 1, value 2 to give us results. It's going to like break all of this into tiny, tiny compartments, into tiny, tiny compartments of value ones and value two that are similar value one, value two that are very similar. It will break it into tiny, tiny compartments. So any new value one and value two that we have is going to be referencing it on this particular data set we have here based on the fast tree algorithm. So it's just an approximation that is doing. That's why sometimes when we multiply higher numbers, we don't get a good result, because if you look at our data set actually ranges from what? From 0 to 100 for value 1, and for value 2 it also ranges from 0 to 100 for value 2. Yes, it ranges from 0. Sorry, I was the one that shifted it to this side a little bit. From 0 to 100 also for value 2. So that's why if I should use a bigger number like 862 times 12, it will not get the accurate answer because it is outside of the training data for multiplication. It's outside of it. And multiplication, as you might think, multiplication is not a very simple, it's not a very simple mathematical model it's not a very simple mathematical operation to model like that. That's the reason why we are just getting really approximate answer. And sometimes we get a very wrong value when we look at very big value 1 and value 2 because it's not in our training data set. So for us to actually get a wide array, a very wide range of accurate multiplication, it perhaps is going to do us a good to include it in our training data set. We have to include more value 1, a higher range of value 1 and a higher range of value 2, perhaps from 0 to 1000 and value 2 from 0 to 1002. But the problem with doing this is that we are going to be having very large values. Yes, we'll be having very large values. Imagine multiplying 1000 by 1000. We'll be having very, very large values that is far away from other values. It might actually cause issue with convergence. But this is actually decision tree. Remember I said that scaling doesn't really affect decision tree model in our previous class. So it might not actually be a problem. That's a way to improve multiplication. For division, you can imagine how division is going to be. Let me open. Let me see. You can just imagine how division would be. Let's visualize division and see how it looks like. Division. Let's div. Okay, div is not here. So I'm going to file. So let's open division. I'm going to open division now. After opening it, I'll share the screen. Okay, a graph. So this is for division. Let me quickly share this division. Okay. So this is the division graph. So this is the training data for division. You can see 1000 divided by 11 is 90 points, 90, 90, 90, 90, 90, like that. This is how I created the data sets for division operation. You can see value 1 divided by value 2 will give us the result. So the AI will try to figure out what is going on here. So now let's visualize this graph on a 3D scatter plot. So we are going to put results as the Y, the dependent variable, then value 1, feature 1, value 2, feature 2. Good. So it's a very strange looking graph as expected. Division is a very, very strange looking graph. So I'm going to share the screen for division. So what you are seeing on your screen now is division. Look at how it looks. See, value 1 and value 2. Okay, good. You can see how it looks like. The division looks very, very strange. So this is the training data that the machine will try to figure out how to do division operation based on this. You can see how it looks so strange. So if you take value 1 now, 1000 divided by value 2, you are going to trace it down until it touches this one of these points here to get our results. So it's based on this that the AI will try to figure out what is going on for division. Okay, now let's look at this from this angle. If you look at division from this angle, it's beginning to make sense. If you look at it from here, you can see how division is kind of like going, and then it goes up a little bit at this point here. So it might begin to, the plane is going to lie on this. The plane, that is the hyperplane for making prediction, is going to lie on this data points that we have here. It will try to touch as many data points as possible. That's what it's going to be using for making division. So this is the reason why it's difficult. Sometimes our division operation is not very accurate because of the nature of division. It's not something that is so simple to model. Looking at this right now, we can tell that it's not going to be a simple thing for the machine to model. So if we are going to visualize it now, let's visualize the model that is used for division. Let's say, let me see if I can open it. If it's in recent, if division is in recent, div model. Okay, so div model is not in recent, so I'll just have to open it. So I'll open division model now. Let's see how division model looks like. Remember, we use fast tree. Multiplication was chosen for fast tree. So let's open division. Okay, so this is division. Okay, so now let me share the screen for division. Okay, so what you are looking at on the screen now is the division model. You can see that it's also using fast tree regression for division model. The same thing happens in fast tree too. It breaks all the similar values, all the similar data points into tiny classes, and then any value 1 and value 2 that we input averaging. All of these tiny numbers are seen here, they are not weight, they are just index of the trees. The trees that is actually used, the decision tree that is used for making approximation. Yeah, I will have visualized it here, but I don't have a software for visualizing it to show how a decision tree works for calculation. So it's just doing approximation for the division. It's not very precise. That's the reason why we're not getting precise values, because it's using a decision tree for making approximate value. So this is the model for calculating this. So anytime we put value 1 and value 2, it uses a decision tree to decide what box of similar value 1, value 2 that is similar to the one, and then use the average, gives us the average. So it knows that, okay, even if it doesn't get it accurately, at least it can actually gives us an approximate value. That is how division is actually calculated. Now, the one that is actually, that I am actually curious to see how it is, I'm sure you are curious also, is the SOHCAHTOA, the trigonometrical function. Let's see how that is visualized. Trigonometrical function is just going to be, it's going to be a 2D graph. I'm not sure if that is going to be, it will actually. So let me open that. Let's open one of the trigonometrical function like SOHCAHTOA. Let's open sine. Let's open sine and see how it looks like. So this is for sine. So I'm going to share the screen for sine. Okay. Let me scatter this. Let me put it on the scatter plot. For some reasons, it's not allowing me to visualize. It's not allowing me to share the screen again. I don't know what's happening. So, okay, this is strange. Okay, I'm unable to share this sine again, but we can still, okay, we can still open the model for sine then, if we can't at least share it. So let's open the model for sine and see. So I'll just go to sine model, SIN model. So all of these things. So what you will have observed is that there are different models for different mathematical operations that is taking place behind. Sub square root square. Okay, cos. I can see sine. Okay, since I can see sine, okay, let's use cos then. So you can try cos. Cos is also a trigonometrical function. So what you are seeing here is cos. So I will share the one for cos now. So what you're seeing here is for cost. Now let's see the model that was. You can see fast tree is also good for cost. Also, the same tree happens too for fast tree. It just breaks down all the data into tiny, tiny compartments, tiny, similar compartments. And then if you throw in a particular value, it then traces it down to a similar compartment and give you the average of that result that is there. So it runs it through the different indexes of the tree, which are the nodes for making decision, and then gives us the approximate. All these numbers that you're seeing here, they are just index for the leaves of the tree. They are just index for the leaves of the tree that we have. So that's what is actually going on for sign, for cost, actually, cost model that we are seeing up here. I don't know why I'm unable to share this. Let me close it all and open it again. Okay, now it's back. Okay, good. So I'm going to, I really want to visualize this sign. Okay, it's back now. Okay. Okay, so I'm going to visualize sign. Okay. I hope it's going to work now. Okay, it's working now. Good. So let me share this window. So what you are seeing here now is for sine. Sine is just a trigonometrical function in mathematics. So you can see the sine of 0 is 0. The sine of 0.5 is 0.008. The sine of 1 is 0.01. The sine of 4 is 0. Actually very correct. How did I do all of this? I also use Excel. There are functions for Excel that you can use for generating all of these values. So I'm going to plot this on a 3D. Remember something, that 3D is 3 dimension, but we only have 2 dimension here, but it's still going to work. It just creates, so for y is the results, and then value 1 is, okay, let's see how it looks like. Okay, good. So I'm going to visualize this. This is very beautiful. Sine has a very beautiful. So you can see what we are seeing on the screen right now is the sine graph. If you remember in secondary school, when they draw a sine graph for us, this is exactly what it looks like for the sine graph. You can see this is actually exactly what it looks like for sine. It's just going up and down, up and down. Although it starts from value. Okay, so the value is going backwards. Let me turn it this way. Come in. This is exactly how the sine graph looks like. Good. So starting from here, good. So starting from 0 to 700 value, and we find the result. Sine 0 is actually 0. Why sine, I think sine 90 or something is 1. If I'm not mistaken, let me see. Yes, I think sine 90. Yes, that's true. Sine 90 is 1. Good. So if you trace it, you will see that you can see the results. Look at the value. The value is almost close to 100, right? I say sine 90. So it will be somewhere here. So sine 90 will be somewhere here. See? It will be somewhere here. If I should trace it here, I'm going to have 1. So what the fast tree is doing is that it's going to break all of this data point, looking at it from the top here. Looking at it from above, it's going to break all of this into tiny, tiny compartments. So there are lots of compartments that is breaking it into. And then any value that we pick that is similar to any of those compartments is to trace it down to the value to give us an approximate answer. And that approximate answer is very, very accurate also. So this is our sign. Yes, this is our sign, our trigonometrical function. So these are the ways in which we actually built my AI calculator that we are seeing here. The first challenge that I faced while building it was this. I tried to combine all the function into the same data set. Do you know the problem with that approach? The problem with that approach is that the graph, our 3D scatter plot, is going to be all over the place. We'll be seeing points everywhere that even a human being looking at it will not know what is happening, not to talk of a machine that cannot think for itself. That's the reason why that approach did not work. So I just tried to combine all the different operations into the same data sets. That is not going to work because they are different. They are very, very different from each other. It's not going to make any sense to the machine, and the machine will never learn from that data set. So how I solved that problem was to separate all this addition, and the one for addition, a different model, the one for subtraction, a different model, the one for multiplication, a different model, the one for division, a different model, the one for square, for power, for roots, for square roots, for power and roots, for SOHCAHTOA, different models for each of it, so that it will be able to know what is going on independently. That's the reason why it was so easy for it to get addition and what and subtraction, very easy for it to calculate it. What I just showed you in the back, that model that I just visualized, what was ran when I click equals to give us this value. When I did subtraction too, the model that I visualized now, what was the thing that ran that gave us this value here. When I did multiplication too, it's using fast tree for multiplication. So it's going to give us an approximate answer. 9 times 2 is 18, but we got 15.56. So it's the compartment that it chose that is similar to 9 times 2. The average of all the data set that falls in that compartment was the answer, 15.56, that it gave us, instead of giving us that direct answer, 18. So that was a major challenge. The first challenge that I actually faced was me figuring out that I had to separate all of these mathematical operations into different model. That was the first challenge that I faced. Now, the another challenge that I also faced was how I was going to be calling different models for different operations. I created a separate class for it. This software that you're seeing on the screen here was actually built with C#. I used C# to build it. Yes, I use C# to build it using .NET MAUI framework. Is for multi-platform. It can work on Android, can work on iOS, can work on Windows, and it can also work on Mac OS. That's the beauty of MAUI, .NET MAUI, and you are able to integrate the machine learning in it. So let me see if I should, let me open it. I'm coming. Let me open it so that you can see what is going on behind. So let's open the behind skin of it and see what is happening. So I'm going to open with Microsoft Visual Studio. I'm coming. Once it has opened, we will visualize, we will see what is going on together. So the class is almost done. So let me just quickly show you the code behind. It's loading now. So you can see how that AI calculator was actually built. Okay. Okay, good. So what you are seeing on the screen now is Visual Studio. Is still loading. To take a little while to load because there are lots of software that are open in the background. I think I have to close. Let me start closing them. Okay. So a lot of softwares are opening in the background. That's the reason why we are not. It's taking a little while to load. Let me close this also. Okay, close that. Let me close this too. So it can load a little bit faster. Let me close this also. So I'm closing some applications in the background. So it's loading now. You can see, very good. So this is the source code of the AI calculator. So it's still loading. Okay, very good. So this is what is actually using. So this is the let's open the main page.
Sir, we can't see it, sir.
You can't see anything on the screen now. Oh,
Yes,
okay.
we
Yeah,
are
sorry,
seeing
I've
the
not shared
image. You
it.
have not
Okay, let
shared
me
it.
share it. Good. What about now? What about now? Okay. Okay, I think I'm sharing it now. Good. Can you see it now?
Not yet, sir.
Okay,
Okay,
let me share.
yes, I have seen it. I can see.
Okay. Okay, good. So this is C sharp. C sharp is a programming language like Python that we can use for creating softwares. And this one is based on .NET MAUI. It's a framework for creating applications that can run on multiple platforms like Android, iOS, macOS, and Windows with a single source code. So you don't have to be building using separate code for different platforms, because those platforms also have a specific programming language that is meant for them. So this is the source code. Now let's open the main page that we are seeing here. Let me open this main page. Okay, still taking a little while. So I'm going to open the main page. Okay, good. So I'll open this. Let me see. Okay, good. So this is the main page. Good. The main page, what you are seeing on the screen is actually displayed by this main page.zam. What we are opening here, you can see is the highlighted one, main page.zam. Main page.zam. This ZAM is just for front end. It's a user interface programming language. It's just like it's a markup language. Yes, extensible, executable application markup language. That's everything. All this code you are seeing here is for displaying the calculator itself. All those text, you can see all the 7, 8, 9, 4, 5, 6 is being displayed here as buttons, the number buttons, as a grid in a grid row. And when you click on it, it's being activated by what we have in the background here, the main page.zam.cs. So this is the C sharp, the code that is running behind for it, for all of our calculations. So we can actually go, there's something I want to show you just to let you know that we are not using the traditional mathematical model for it. So I'm coming. Let's see how. You can see now. Let's see, for instance, for it to calculate this trigonometrical operations that you are seeing here, you can see what is here. The To perform trigonometrical calculations, this is it here. The result is equals to model call dot predict. You can see the predict here. It means that there is a machine learning model that is making the prediction for the trigonometrical operations that is happening behind. That is what is happening here. At the end of the day, it will output our results for us. That's what is going to happen to string, it sends it back to the results, to the front page itself. That's for trigonometric function, to show that is a machine learning that is predicting it. This is not the typical way to program a calculator. This is just for educational purpose. Now, to calculate the square, the same thing too is also calling a model call dot predicts here. What we have here, dot predict for square. The same thing for square root too. Model call dot predicts. The same thing happens here too. For other operations also, let's check other operations that is happening. Those are not the only ones that is using to actually calculate. Let's see. For calculate results, I'm coming. This is for setting operations, for other operations. So we go to where set operations is. Set operations. This is just to set it, to let it know which operation to actually use. Operations OP, I'm coming. Square roots. Then to clear the display, to add, to calculate result. So this is it. For calculating the results. model call dot predict for calculating results. So it's predicting the results using machine learning model. Is not actually the traditional mathematical libraries that we use for it. So let's open this model call. Let's see what is in this model call. So this is the model call class. Is the one that actually calls all the different models for the different operations. You can see for addition, this is what it uses. It uses the add model input and outputs, add prediction engine. For different ones, it calls it for the different ones. For addition, for subtraction, for multiplication, for division, for square root, for square, different models for different mathematical operations. And this is where it's loading it. You can see .zip, the ones that we visualize. Anytime we are trying to load the addition prediction engine, for instance, it loads the model, the addition model, which is stored as a zip file. Add model.zip. We have already visualized it. Anytime it calls the subtraction, submodel.zip. Anytime we try to multiply, it loads the model. Mol model.zip is also loaded. And this is for the training. In case these models are not there, all these add model, sub model, more model, deep model are not there, this is what it uses to train it. You can see it takes the training data, add CSV, is a CSV file, and then saves it as add model.zip. And then displays add model, say trained and saved successfully. It does the same thing for this one too. Uses the training data to create this model file. This is the training data to create. It does it for all the operations that we are seeing, everything, the tan, the sign, training the model. All of this has been coded behind it. And let's open the training data itself. You can see the training data. Let's open the addition training data. It's still loading. Aha, you can see it's a CSV file, which is what you are seeing here. CSV just means comma separated, value 1, comma, value 2, comma, results. Then the next line, -4 plus this one plus give us. So this is the training data set that it uses to train and to create the model file. There's one for add, for cost. There's one for division. There's one for multiplication, as you can see in all of this place. So let's open the one for add, this add model CS. Let's open the model that gets called anytime we do addition. This class actually gets called anytime we do addition. So it will load the first column. That's the first value 1. It loads the value 2 into the second column, and it loads results into the third column. Indexes actually starts with 0, just as in Python too. Python index starts with 0, 0, 1, and 2, the index that I was talking about. This is the add model output. Is outputted as is actually score within the model. The column name within the model is called score, but is being called as a result here. Is being get and set as a result. So that's the result you're going to see anytime you press the equals to. You can see. Now let's see how add model was trained. Add model was trained here. Look at the pipeline for training add model. You can see it's using a regression trainer, SDCA. That's stochastic dual coefficient ascent. That's what SDCA means. It's a regression trainer for add. The same thing for subtraction. Let's check what subtraction looks like. The subtraction class, the same thing, loads value 1 to column 1, value 2 to column addition. You can see regression trainer is a regression. It uses regression trainer for it. It's just a simple regression. That is it for subtraction. For multiplication is not just a simple, it's not something very simple like that. You can see multiplication is using fast tree, and it has hyperparameters too. You can see the number of leaves, 147. Those are the nodes. The minimum example per leaf. These are the hyperparameters, the number of trees, 2523. That's the division branch, the things that branches into different nodes. That's the tree. The maximum bind count per feature, the feature action, the learning rate too. Yes, there's something called learning rate. It's an hyperparameter, the rate at which learning takes place. That is the rate at which the weight and the bias is being changed gradually. is quite low here. So the question you would ask me is, how did I figure out the hyperparameter to use to get the best results? Well, that is where auto machine learning comes into place. Auto machine learning is useful for people who are just going into machine learning for the first time, and they don't want their head to explode hyperparameters at the same time. So you can see I just clicked on add and I click on a machine learning model. When I click on that, I'll be able to add my training data to it. Let me add. I'll be able to add my training data, and then it will pick the best hyperparameter for me. It will pick the best algorithm for me. It will pick the best features, the best tuning for the algorithm that gives us the best results. And how does it know the best results? You guess right, it's the mean squared error. Either you use the mean squared error or you use R squared, whichever is most appropriate for your project. So it's loading now. I just want to show you something, how I was able to figure out the right hyperparameter to choose. Is what we're going to select. We are going to set the training. The training environment is my local CPU. Then the file is CSV, comma separated, task separated, or just a simple text. Or you can also use a SQL server if your training data is on your SQL server. But in this case, we are going to use a simple data source, which is my text file. So I will just go to my AI calculator. And then let's pick on addition. Addition is a very simple thing to figure out. It's a very simple operation to model. So you can see addition has been loaded now. So I will now select the column, our column, to predict the label. You know what the label is? The label is the dependent variable, which is the result. The result is what we are trying to figure out. Then I'll open this advanced data option. None of it is categorical, so I won't select anything here. Validation, cross-validation means that's another class. That's another thing for another class. This split training test is just to split our data, 80% for training, 20% for validation. That's what happens in cross-validation though. But the difference between cross-validation and split is that cross-validation just like it picks different training validation sets. It picks up to 5 different training validation sets from the same training data, so that our model is not going to be too fit to a single train and validation set alone, just to make sure that it doesn't overfit. That's what that cross-validation is all about. So the result here is what we're trying to predict. And then the training time, you can pick in seconds. You can pick 100. Let me just show you 100 seconds for us to see, or let me make it 150 seconds for training. And then I can go to my advanced training option. You can see, now this is the metrics that the model will use to find the best performing model. The metrics that I was talking about. You can see that there's mean squared error. The closer to 0, the better. There's the R squared, is also another metrics. The closer to 1, the better. And then there's also root mean squared error too. Is also a metrics that you can use. But the ones that we taught in our previous class was mean squared error. So we're going to stick to the mean squared error. So the trainers, these are the algorithms that will be used. The algorithms are the ones that would figure out the type of calculation that is going to be happening behind. All the mathematical calculation, all the decision, all the rule-based algorithm, the stepwise things that is going to take behind. That's what the algorithm here we selected. We want to use fast tree, we want to use fast forest, we want to use light GBM, we want to use BFGS. This BFGS is a very funny name. It's named after the people that founded it. The stochastic dual coordinate ascent. These are the algorithms. And then for the tuner is the ones for selecting a right hyperparameter to use. An example of an hyperparameter is the number of trees, number of leaves, the training rate. Hyperparameters are the things that the machine cannot determine by itself from the training data. That is what an hyperparameter is. So we have to set the hyperparameter by ourselves, or we can use AutoML to set it. That is automatic machine learning. So it's going to be based on SACFO. That's the default one that is used by this our AutoML from Microsoft. Or we can also use cost frugal for selecting the hyperparameter. So this hyperparameter will determine the number of trees, the number of leaves, the learning rate, the feature segmentation, all those things, all those minimum counts, minimum feature per tuner. The hyperparameters, the things that the machine learning cannot learn on its own. And then there's a stop strategy. That is, you cannot train forever now. If you train forever, you run out of memory. So you have to pick 150 seconds for it, or you pick the maximum number of models to explore, or the maximum memory to use. And then there's a sample strategy. This sample strategy is if you have a lot of data and you want to just use a small sample of it at a time, so as you will not run out of memory soon enough. That's what they all means. And then you save. And once I click save and I click on start training, you see what is going to happen now. So start training, you can see available trainer, the evaluation metrics, and then it starts measuring the MSC. Is using different algorithm. You can see the AutoML is doing all of this for me. So the AutoML will select the best algorithm with the best hyperparameter that was trained at the shortest amount of time. You would agree with me that the most accurate algorithm that took the least amount of time is what we want, because we don't want to spend years training our data. We want to get the most accurate result in the shortest amount of time. You can see all these numbers that you are seeing down here. Let me bring it up. All these numbers that you are seeing here, they are the different algorithms that is being tried out. So for someone that is new to machine learning, you don't have to start bothering your head trying to figure out, should I use SDCA? Should I use fast tree? Should I use fast forest? Should I use light GBM? Should I use XGBoost? Which one should I use? Should I use it? Should I use that? What about the hyperparameter? What's the number of leaves will I use? What's the number of trees I'll use? What's the number of features per this I'll use? All of those things is going to be determined by the AutoML, and it's going to be measuring the MSC. So the one with the lowest MSC will be the one that will be selected. The lowest MSC and the shortest duration will be selected. So you can see what is going on here. So you can see it has already selected the best one. The best one is the stochastic dual coefficient asset regression for addition. It has selected the best for us, and it has explored 37. So this is how machine learning is being applied in a standalone software. So that will be all for now. I can quickly go over it. I can stop the training now. It will generate the code for me. So you can ask a question if you have any.
All right. Thank you very much, Adedapo. Does anyone ask a question? Do we actually understand what Adedapo taught us this evening, or it looks like a magic? I need a response, please.
Well, I think it's just something that we would need to just work on. Thank you so much, sir, for taking our time for us. It was it's such a moment of insights. We got so many insights, and then I just want to ask: is it possible, like on a personal note now, is it possible I could connect with you, sir?
Yes, sure. You can message me if you need to. You can. Definitely.
Thank you, sir.
Yeah, there's a lot. The learning curve is actually quite steep. I agree. So there's a lot to learn there, but this is just to give you a good start on where to can lay your foundation on moving forward.
Okay, sir. Thank you, sir.
Sure.
Okay, so
yeah, good. Hello, sir.
Yeah.
Can you hear me, sir? Yeah. Good evening, sir. Thanks
Yes, sure.
so
I can
much
hear.
for this opportunity. I really enjoyed and appreciate it. But there is a question I want to ask, because though I'm a newbie to machine learning, and I was just trying to see if I could, let me say, beginner. So I want to ask, because I have been, since I started my learning, I've been using Anaconda, Jupyter Notebook, and Collab. I mean, the Google Collab. So I've been using them.
Yes, yes.
But when you brought us to VS Code and all those things that we are doing in when we want to do the training, and what you just
Mhm.
used in training the the machine now, I just look at it that is somehow is still is like a trick to me. So I don't know, is it that we need to install some extension in VS Code if we are to use this particular this we are going to go by the way you trained us today, as in I'm talking about the last aspect of using the
Yeah.
data set to
So
train the machine. So
yeah, there's the AutoML is separate. You have to like it's like an extension, like you said, but it is very compatible with Microsoft. It is a Microsoft product. This AutoML for Visual Studio. Yes, you can actually install it with this Visual Studio installer. Yeah, there's a software. You download it and you install it. Visual Studio installer. Yes. So this class was just to show us a real life application of machine learning. Most data scientists do not really bother on creating a standalone AI software because what their duty is just to create a machine learning model on its own that is going to be run on Jupyter on a kernel, like a Jupyter notebook, as you said. So, or you can also run it on this cargo if you want. Like if you want to run it on the cloud, if you don't want to run it on your PC, you can run it on cargo, which is a kernel. So most data scientists do not really like go into AI softwares on their own. But for those who want to make a standalone software that is wrapped around the machine learning model to have a proper AI software, they might actually need to install they will need to install Visual Studio. Visual Studio is an integrated development environment for making software, and you can integrate machine learning model into it. So it's just like wrapping a software around your machine learning model. But a data scientist just needs to create a model and give it to probably an AI engineer. An AI engineer will not be the one to go and code everything, and then they work hand in hand with a software developer, and then they'll now put it in a standalone software that uses AI behind it. So that is what we are just trying to show. We are just trying to show a practical use case of it, of an AI.
all right,
I hope
thank
I've been able to answer the question.
you. Yes, sir.
Oh,
All right.
okay, so let me just let me just clear about what Adedapo did. Though I expect a different approach, but let me just explain to us. I know some of us on this call, like Kabiru Lawale and some other people would be able to relate with what he did. But the AutoML is actually a codeless approach to um, training the data. Okay, it's just like you want to train a data set, you don't want to start coding by yourself. Just feed it with the data, and it does select the. You see him selecting the hyperparameters, selecting different things. Once you select all those things, you just train the data for you, and you have your machine learning model. Okay. So what you said, Sylvester, you're still on course. I think for beginners, a lot of beginners start with you have a Jupyter notebook when you import a structured data set, and you write different code, you clean, you do the ED and some other things, and then you train your model. Okay. So I don't know Adedapo's plan, but I think if you could go by a bit, because to me, when you were doing it, I was like, Adedapo, we started with simplest, but it's going a bit advanced. Some people on this call might find it a bit difficult to catch up with. So I don't know if it's possible for us to now we are able to see a situation whereby if you don't want to stress yourself, just finish your data to AutoML, they draw the training for you. But I feel compelled that for the starter, you know, like just like what you have, what do you call it? This large language model, this common
Yeah.
GPT.
LLM, ChatGPT.
Yes, the chat GPT. You know, you could write a code.
Yes.
You want to, for example, you want a code for calculator. You could just type it, write me a code for calculator. ChatGPT will populate the code for you. Okay, but as long as we have all those things helping us, you know, I always encourage people that are just starting to start from the basic. You know, when you know what is going on from behind, you know, you're able to relate with what you call it, the software that will help you in your work as a machine learning or data scientist eventually. So I don't know if it's possible for us to I think that we understand what I'm talking about now. To go back to that traditional way of maybe getting the data set, importing it to Jupyter Notebook. You can use choose to use
Yes, I get.
Visual Studio. Visual Studio is another platform to train your machine learning. So,
Yeah,
but
sure.
a lot of people use Jupyter Notebook because, you know, on Jupyter Notebook or Google Colab, you can write comments, you can, you know, do a lot
Yeah,
of
sure.
put a lot of pictures and some other things to explain to the
Yeah, sure.
audience. So I don't know if
Yeah.
it be possible, at least maybe for the next 2 or 3 class we have, you can have a data set imported to the Jupyter Notebook. Then we train with different algorithms, like maybe support vector machine.
And see how it looks
Linear.
like. Yeah, I get it. Sure,
Yes,
sure.
yes, yes,
Mhm.
yes. So this
Yeah.
approach is not a bad idea. Don't get me wrong, please. It's not a bad idea. At least for people on the call today, they know that there's something that can help you once you know what is going on behind. If you can
Yeah.
also relate people that are on this call, you can relate back in the days when you have when you used to when you were learning HTML. You know HTML, you have to
Mhm.
write HTML tags, put CSS, all those things. But when the Dreamweaver come,
Mhm.
I think it's Dreamweaver. Yes, Dreamweaver is just like drag and drop to build your website. Just drag and drop. Then go and check the code behind.
Yeah.
All the code, you don't have to
Yes,
stress
yes.
yourself. Yes. So
Yeah.
thank you very much. So I don't know whether you
All
have
right,
anything
so
to say before we call it a day.
all right. Thank you guys for attending this class.
So please let's appreciate Oladapo. It take a lot of. I know it's a very busy guy. You know, take a lot of effort to put all these things together. It's not easy. So let's please appeal. I could see emojis already. Thank you very much. Thank you.
All right,
Thank
so
you
thank you
very
very
much.
much.
On Monday, right? I hope you not get lost in coding again, because a lot
Ah,
of time.
I'm not sure.
We are
Let's hope so, Sha. Let's hope so. Let's hope
okay,
so.
because we are meeting
All
a
right,
lot of
so
classes, and you know, by the middle of September, I mean, we are in September, right? Are we in September or
yeah, I
October?
thought you said someone wanted to take over, like someone wanted to take over the next class, the
No, no,
classification.
not next class. I'm talking the middle of September. Somebody else will
September.
take over the
Okay.
classification,
Okay.
classification
Oh,
aspect of
okay.
machine learning.
All
Yes.
right.
So still have like I
Okay.
think like
No
2 or 3
problem.
classes to help us with.
Yes. Sure.
Thank you very
All
much.
right
Really
now.
appreciate your
Okay
time
now.
and your
No
efforts.
problem.
Thank you, Sal. Thank you so much.
All right now. You're welcome.
Bye, everyone.
Yeah, bye.